Okay, I think it's going. So we have worksheet today called Mr. Bean's Wild Ride, and the test is going to be actually in a large part based upon this worksheet. So it would really behoove you to make sure that you're making sense of this worksheet and really know what you're doing because the test is like literally there's a couple pages, maybe 3 of the 4 pages are based upon this worksheet, which is mainly using Newton's first and second laws. So this is called Mr. Bean's Wild Ride, and so here we go. I'm going to explain it, and then if you look at the quiz goes along with the um, with the questions, but they're not the exact same questions, so be careful with that. So what we got here is we have a picture of Mr. Bean in his awesome car, and then we have 4 scenarios of force diagrams, and you're supposed to be able to figure out what happens with these force diagrams. So let's go ahead and take a look at what happens. Let me see if I switch screens. Yeah, I'm still in the corner there. That's good. So I'm going to have to stretch out a little bit in a sense here. So what do we have here going on? We have Mr. Bean's Wild Ride, and it says for this worksheet, Mr. Bean and his car have a mass of 400 kilograms. I'm going to move this a little bit so I can get to it a little better. A mass of 400 kilograms. And we're going to use -10 instead of -9.8 for little g. So it says for each of the following questions, draw a complete force diagram and answer the accompanying questions. Number 1, Mr. Bean and his car is sitting at a stop sign. Draw the force diagram and explain which of Newton's laws applies to this situation and why. So he's sitting at a stop sign. So the first thing we do is we draw a dot to represent his car, and then we draw our little force going down. This force is the force of gravity. So hold on one second, and I'm going to double check something. Force of gravity. Okay. And so the force of gravity is equal to m times g, and the m is 400 kilograms. And g, of course, is a -10 newtons per kilogram. The kilograms cancel, and we get Fg is equal to a -4,000 newtons, and that's Fg. He's not falling. So in this case, um, that line right there would just indicate that if it was like that by itself, he would be falling, and he's not. So we must have another force up, which is the same size. And so that force is Fn, or the normal force, the force that's coming off of the surface of the ground. And so that normal force is equal to a positive 4,000 newtons. And a lot of y'all are struggling with that a little bit. I shouldn't put those little tick marks there. I should just put, that was an equal sign, but positive 4,000 newtons. Now, the reason this is true is because it's not falling. And so the net force in this case is 0. 4,000 down, 4,000 up is 0. It's going to be kind of hard to draw things exactly to scale in this quiz because the mass and the weight are very large, and then some of the sideways forces won't be as large. So it doesn't have to be perfectly to scale, but hopefully we'll get the idea. So in a car at a stop sign, you might have no forces on it, sideways forces. Of course, you're going to have an up force and a downward force and the force of gravity and the normal force, but you might have no sideways forces on it. If you have a stick shift car, and his car is stick shift. So you could possibly, in some cases, take your foot off the brake and just sit there. But in most of our cars, there's going to be a little tiny applied force this way which is your engine trying to make you kind of idle forward. And then, of course, you're not moving, you're at a stop sign. And so there'll be a little force in the opposite direction, which is going to be the force of friction. And that is going to be your brakes. And so, and this will be your brake is it's in drive, not your brake, but your car is in drive. So it says draw the force diagram and explain which of Newton's laws applies to the situation and why. And so the question you always ask yourself, is it balanced or unbalanced? And so this thing is balanced. And when we say balanced, of course, we mean that the net force is equal to 0. And therefore, we also know that the acceleration is equal to 0. In this case, we know that he stopped. So in this case, we're going to say it's Newton's first law, because whenever it's balanced, it's Newton's first law. And we have this idea: an object at rest stays at rest unless acted upon by unbalanced forces. And we already said that the forces on this are balanced. And so the net force is 0. It's got 0 acceleration. The initial velocity is equal to final velocity, and they all equal 0 meters per second. That is the first part of the question. So as we go through this, hopefully you get the idea, and it's just going through the things we went through previously. So let's do the second question. Now Mr. Bean steps on the gas and applies a force of 1200 newtons for a period of 5 seconds. Assume that there's no friction over these 5 seconds. Now, there will be friction, but we're going to assume that there is no friction. Draw a force diagram and explain the Newton's law that applies here, and calculate the amount of acceleration he will have. So once again, I'm going to draw the force of gravity going down. I don't have to repeat the calculations because I already know it's a negative 4,000 newtons. And I'm going to repeat the normal force going up is a positive 4,000 newtons. But in this case, it says there's an applied force of 1,200 newtons. So I'm just going to draw it like that, although it's not perfectly to scale. I'll draw that is FA equals 1,200, not 12,000, 1,200 newtons. And there is no force of friction. And you notice there, since there's no force of friction, I'm not going to draw the arrow. There is no friction. So it says draw a force diagram and explain the Newton's law that applies here and calculate the amount of acceleration he will have. And so this is not Newton's first law. This is Newton's second law. And because, is it balanced or unbalanced? It is unbalanced. And if it's unbalanced, there is going to be an acceleration. In this case, we're going to find out what the acceleration is going to be. What we know is that acceleration is equal to net force over mass. And in this case, the net force is quite easy because there is no opposing force. And so we have 1,200 newtons over 400 kilograms. And 1,200 divided by 400, I can cancel out these zeros, and I get 12 divided by 4 gives me 3. And you would think, okay, it's Newton kilograms. Now remember, the units of Newton is actually kilogram meter per second squared. So the kilograms actually cancel, and you get what you thought you should get, hopefully, is 3 meters per second squared is my answer for acceleration. All right. Not quite done with this question, because it says after these 5 seconds, calculate how fast Mr. Bean will be going. So I look at my equations and I'm thinking to myself, okay, what do I have? I want to know how fast. That is my unknown. And my unknown is VF. I know my acceleration is 3 meters per second squared. And I know my VI was equal to 0 because I was at a stop sign, meters per second. And I also know my T is going to be 5 seconds. So do I have an equation that fits perfectly with this stuff? And yes, of course I do. Fits perfectly. VF is equal to A times T plus VI, equation number 2. So how fast will I end up going is VF. My A is 3 meters per second squared. My T is 5 seconds. My initial velocity was 0 meters per second. My VF is going to be equal to 3. The second cancels one of those. I get 15 meters per second. And this is 0, of course, so I'm done. So after those 5 seconds, I wound up going 15 meters per second. Question number 2 is done. All right. Question number 4. So as Mr. Bean continues to accelerate, let's assume his friction increases to an average of 400 newtons over the next 10 seconds. So now, and that's true, when you're going very slow, excuse me, when you're going very slow, you'll have less friction. The faster you go, your friction will build up, the resistance will build up, the air resistance will build up. And so air resistance isn't really exactly friction, but it's the same thing. It's an opposing force. And so now his friction and air resistance is going to increase to an average of 400 newtons over the next 10 seconds. And so now it says draw the force diagram and calculate how much acceleration we have. Now, do I need to ask you what is this, whether this is Newton's first law, Newton's second law? Maybe it's a good question. All right, so now same thing. Weight hasn't changed. Fg is equal to negative 4,000 newtons. Fn is equal to a positive 4,000 newtons. And as he continues to accelerate, so he's still going to keep his foot on. And so that's the applied force of the engine is going to be 1,200 newtons. But now the force of friction has increased to FF equals 400 newtons. All right. So now calculate how much acceleration he will have. So once again, this is unbalanced. And unbalanced means that it's Newton's second law, which means he is going to accelerate according to this formula. So my net force in this case isn't going to be 1,200 newtons. It's going to be 1,200 newtons minus 400 newtons. And technically, this one's positive, this one's negative, so this minus this. Be careful, because some students don't really realize their mathematical equations, and so they'll say 1,200 minus a minus, and that will be plus. That's saying that these two are adding together. They do add together if they're the same direction, but these are not the same direction. They're opposite directions. So no matter what, if they're opposite directions, they're gonna subtract. Like for instance, this is 4,000, this is 4,000. Those are the same. They're gonna cancel. 4,000 minus 4,000 is 0. Or you could also say 4,000, a negative 4,000 plus 4,000, right? Or you could say 4,000 plus a negative 4,000, and that will give you 0. These two cancel out. These two do not cancel out. They're not balanced. So that's 1,200 newtons minus 400 newtons over my mass. My mass is the same as before, 400 kilograms. These don't cancel. You can't do that, right? So I'm going to carry it on down here. 1,200 minus 400 is going to give me 800. So now I have 800 newtons. This is coming over here now, over 400 kilograms. And so I get 800, and the zeros cancel. 8 divided by 4 is 2 meters per second squared. So now I'm still accelerating, but I'm just not accelerating as much as before because my force of friction, my drag is increasing. So now it says, after this 10 seconds is added to his previous speed, calculate how fast he will be going now. So in this case, I got my same idea. I got my unknowns and my knowns, and my unknown is VF once again, how fast he will be now be going, right? But now I have 10 seconds further, so my time is now 10 seconds. And my acceleration is not 3 meters per second. My acceleration is only 2 meters per second. And my VI is not 0 anymore. My VI is 15 meters per second from the previous question. So this can be a kind of a confusing worksheet, but it will be the same way on the test. If you're following along with the story, it's not that confusing. Mr. Bean is at a stop sign. He's not moving. Mr. Bean begins to accelerate with very little friction, zero friction in part 2. And then we get on question 4. He's still accelerating, but his friction is building up. Oh, I think I was going off the page there. Now you see it. So after this 10 seconds is added to its previous speed, calculate how fast you'll be going. My final velocity is what I want to find in the next 10 seconds. My acceleration has dropped from 3 meters per second squared down to 2 meters per second squared. But now I have an initial velocity of 15 meters per second. So same equation as before, because this solves the question, how fast will I be going? Equals AT plus VI. I'm trying to write really neatly. This is what we do in physics. VF is what I want to know, so I just copy down my unknown. A is now 2 meters per second, and that's squared, times my time, which is 10 seconds, plus my initial velocity, which sometimes is 0, but is not 0 in this case. So this is 15 meters per second. The second cancels there. I get VF equals 10 times 2 is 20 meters per second plus 15 meters per second. These are both meters per second, so I can just add them right up. Equals 35 meters per second. Side 1 done. Okay, side 2. Side 2 gets a little bit more difficult, I guess, if you want to look at it that way. Interesting. Side 2. Okay, now Mr. Bean is cruising down the highway, and although he's still proceeding with the gas pedal, applying 1,200 newtons of force, he has now reached a state of dynamic equilibrium. Put your thinking caps on. Draw the force diagram and explain what does that mean with respect to Newton's laws. Dynamic equilibrium. How am I going to draw this force diagram? Dynamic equilibrium. So this word dynamic equilibrium, what does that mean? It means that it's balanced, right? But moving. All right. So let's draw the force diagram as it says. So once again, I've got this force down and I've got this force up. They are equal. The force up is the normal force, and that is, what was that? 40,000? 4,000? 4,000 newtons. And then I got the force down. The force of gravity is a negative 4,000 newtons. And now it says I'm still proceeding with the gas pedal applying 1,200 newtons of force. So I still have FA equals 1,200 newtons of force. But it doesn't tell me anything else. It just says that's how much force there is. It says draw the force diagram. It's in dynamic equilibrium. So this is a catch you start type of question on the test, right? What happens? So since I know it's balanced, because that's what dynamic equilibrium means. Equilibrium literally means equal, right? Equilibrium. These two are equal, so my net force in the vertical direction is 0. I'm moving at a constant velocity, right? So maybe I should take these out, right? Moving, and I should say that at a constant velocity. So, all right. So that means if that's true, my net force has to be equal to 0, my acceleration has to be equal to 0, and we have to have Newton's first law again, right? Newton's laws, Newton's first law. Newton's first law, wait a second, it's got to be balanced. This must also be 1200 in reverse. So that is true. The force of friction will actually rise. Think about it. You're on the little light, you know where Cattleman's is? Right on Taylor. So you're on the little light going on the freeway. You turn right, and there's a little, what they call metering light. The metering light is on, 2 cars per green, right? It turns green, you start to go, you push the gas, you begin to accelerate, and then as you get faster and faster and faster and faster, you're not going to accelerate to infinity, are you? No, you can keep your foot at a very specific spot in the gas pedal, and it no longer accelerates. It will go at a constant speed, let's say 65 miles an hour, since the speed limit there is probably 65 miles an hour, right? So that's what's happening right here. Your foot is on the gas, that's the applied force of the engine, and the force of friction must actually be equal to it in the opposite direction. If this is greater, you'll slow down. So if you take your foot off the gas pedal, what's going to happen? This will get less and you'll slow down. If this is greater, then you'll speed up. So now it's 65, but maybe I want to pass this truck. This truck is maybe dangerous. So I want to pass the truck. So I'm going to take this up to 1300 now. And if I take it to 1300, it'll be a little higher than this and I can pass the truck safely. All right, so this is Newton's first law. Dynamic equilibrium, though. So Newton's first law with dynamic equilibrium is a little bit different. We say it the second way. An object in motion, and there's a couple ways to say that. You could say we'll continue it in motion, or you could say we'll maintain constant velocity. An object in motion will maintain constant velocity unless what? Unless acted upon by unbalanced forces. And these forces are balanced. And so that is Newton's um, first law. So since the forces are balanced, it stays the same speed. In other words, it stays the same speed. Okay, number 7. Now, let's just say, it's not part of the previous map, but let's just say that the car is now going 40 meters per second. If Mr. Bean lets off the gas entirely and applies his brakes, draw the force diagram and calculate what force would take him to stop in 10 seconds. It's actually a little harder question. It's actually a little harder question. In fact, it's a two-part question. This is the type of question normally reserved for AP classes because I'm asking you a question that you can't answer directly. You have to answer it indirectly. And I probably will make it a little bit easier on the test itself. So in all these things, you probably should try to do. You should probably pause the video and try to do it on your own, and then see my solutions afterward. Probably on every single section of this, that would be a good idea. So go ahead and pause the video, and then and try it, and then let's do it. So apparently you're back now. All right, so let's see the car is now going 40 meters per second. If Mr. Bean lets off the gas entirely and applies the brakes, draw the force diagram. Okay, so force diagram is going to, once again, look a little bit like this. I'm going to have the force of gravity, negative 4,000 newtons, and up I have the normal force, which is a positive 4,000 newtons. And it says he lets off the gas entirely. So how much force do I have going this direction? None. He lets off the gas entirely. So FA, I don't have to draw this. I'm just showing you that there's no FA. So he would begin to slow down automatically because of friction, air resistance, right? But I wouldn't count on that if I'm going to come up to a stop sign. So I need to stop within 10 seconds. So I need to hit the brakes. And so the brakes are going to obviously be that way because his velocity's that way. Velocity's to the right, brakes are to the left. It's going to slow him down. So this is also the force of friction. You don't have to call it the force of the brakes. The brakes is actually providing friction to a disc or to a drum, depending on whether you have drum brakes or disc brakes. And so how much though? So how much force is this? Well, that's kind of a hard question because the force is going to be equal to, so in all these equations, another way to write Newton's laws is to say force is equal to mass times acceleration. That's Newton's second law. Just another way to write it, right? I know my mass. My mass is 400. That hasn't changed. So my force is equal to 400 kilograms times A. And I go, okay, what's A? Is A given? A ain't given. So, but so A is actually an unknown. A is an unknown. But it does say, what do I know? It does say I'm going at initial velocity of 40 meters per second. And he applies the brakes for 10 seconds. And what else do I need? Well, I'm going to stop, right? What's my final velocity? Vf equals 0 meter per second. So what equation would go with this? So A is actually equal to change in velocity over time. Change in velocity is defined as final velocity minus initial velocity over time. This is equation 2. It's on your equation sheet. I'm not sure what else to say about that. I'm not sure what to say about that because it looks like there's two different versions, but it's the same thing. You gotta know that this is this. So VF is 0. Be careful with that because so many people will put 40 minus 0 is 40. This isn't 40 minus 0 is 40. It's similar. It's 0 minus 40 over a time of 10 seconds. And so this is a negative 40 meters per second over 10 seconds. And this gives us a negative 4 meters per second squared. And so now we know this is the A. And now I can drop that A in there. Negative 4 meters per second squared. So that's a two-step problem. You can't do this first. You got to do that first. And that's a little bit difficult, right? So F equals a negative 1,600 newtons. I know it's kilogram meter per second squared, but you also know it's a force. And so this would be a negative 1,600 newtons. And it makes sense. 1,600 divided by 400 is 4. This is 0. So the acceleration is 0, right? Right? What about here? The net force here is 0. So the acceleration is 0. What about here? 1,200 minus 0 divided by 400 gives me 3 meters per second squared to the right, unbalanced to the right, accelerating to the right. 1,200 minus 400, right, is 800. 800 divided by my mass, it's my net force of our mass, is 2 meters per second to the right. This one, 1,600 negative minus 0 gives me a negative 1,600, and a negative 1,600 divided by 400 will give me 4 meters per second. So if I want to plug it in the other way, I can also say that. I can say that 4 meters per second squared equals, negative 4 meters per second squared, and this is me checking myself, equals 1,600 newtons over 400 kilograms. That's coming from that idea that A equals F over M. Yeah, that makes sense. It's the same thing, right? This is just another version of that same equation. I just rearranged it, right? Remember, A equals F net over m. So I was just checking myself just to say, hey, yeah, that does make sense. All right. Last question. Most difficult. Maybe I should make you do this one on your own. Maybe I should make you do this one on your own. I don't know. All right. Do it on your own. I'll keep talking, but you pause the video and do it on your own. All right. Finally, Mr. Bean has picked up his big friend who lives across town. Mr. Bean now has the bright idea that he can calculate his big friend's mass using his speedometer and a stopwatch. Mr. Bean is crazy into physics. See if you can calculate this for him. So the car changes from 0 to 8 meters per second in 4 seconds. He has stepped on his gas pedal, headed back home, slightly harder than before at negative 1400 newtons. Assume that there is an average of 200 Newton resistance against the car. Try to calculate the big friend's mass. This is a 4-part question. Actually, it's probably a 3-part question. All right. So what we got here is we have our force diagram just like before. But in this case, the problem is we don't know Fg and we don't know Fn. We know they're equal, but we just don't know what they are because it was 400. That's with Mr. Bean in the car, but now Mr. Bean's big friend is in the car with him. So what he's going to do now is he's going to go back home, and we're going to assume this is back home. How do I know it's back home? Because it's a negative. So left is back home. So this is not the force of friction. This is the force that's applied now is a negative 1400 newtons. Okay. And then we have a force this way. That's the force of friction. The force of friction always opposes motion. So he's going back home, right? Where's my camera? That doesn't work that way. Okay, he's going back home that direction. And so that's negative, and that's the direction home is. Friction is always against it. So friction is always going to oppose motion. And so the friction is, where is it? It's 200 newtons of resistance. This would be like an A question on the test. This is a good one. So it's 200 newtons. Okay. So what do we know? We do know the net force. What's the net force? So the net force in the vertical direction is 0. We don't know what this is and what this is. We just know they cancel out. But the net force in the horizontal position, so the net force in the is to the left, right? Net force is to the left, and it's equal to a negative 1200 newtons. Now remember, the mass is not 400. The mass is different now. Okay, what else do we know? We also know that, does it say it's acceleration? It doesn't say it's acceleration. We need to know what the acceleration is. And the problem with acceleration is we can't get it from this because we don't have the mass. So we don't have the mass equals question mark. We don't have the mass. We also can't find the acceleration going with the force equation. But can we go for the acceleration using the unit 1? You remember how acceleration, there's 2 ways to think about it. There, what causes force and what causes acceleration, forces, and what is acceleration? Well, acceleration is change in velocity over time. So acceleration is change in velocity over time. It's the most basic definition. Acceleration also is caused by force. So what was the change in speed? So let's see what it says. It says the car changes from 0 to negative 8 meters per second in 4 seconds. So it is going to change a negative 8 meters per second, and it's going to do it in 4 seconds. And so actually, when you look at it that way, it's actually pretty easy to find the acceleration. You just couldn't do it using the force equation. You couldn't do it using Newton's laws. So the acceleration in this case is going to be a negative 2 meters per second squared. Okay, so that was pretty easy. It was just kind of hard to think of it. Think of how to go with that. Okay, so now what's next? So what's next actually is to put it back into our other equation, which is what is the 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 mass here, right? I want to find the mass. And so how do I find the mass? Well, we're only really looking at the sideways. We're not looking at the vertical yet. We're only looking at the sideways. And in the sideways motion, this mass is what's called inertia. And inertia resists motion. So I have this equation that says F net is equal to mass times acceleration, and that's my inertia. In this case, I want to find the mass, right? So do I know the net force? I do know the net force. Do I know the acceleration? I do know the acceleration. So now finding the mass will be really easy. I'm going to rearrange this so that I have mass is equal to right here. Mass is equal to force, the net force, and divide each side by A, and I get M equals F net over A. That you don't see that equation written like that very much, but it's just a third variation. The third variation, is that a 3? A third variation of the, it's weird because my camera's over here, I'm writing over here, of the Newton's second law equation. It's just rearranged correctly algebraically. So my mass is going to be a negative 1200 newtons divided by a negative 2 meters per second squared. And my mass is going to be equal to 1200 divided by 2. The negatives cancel. A negative over negative is a positive. So my mass it has to be positive because mass is not a negative value. Is 600 newtons. Okay. Last step. So what is the weight of the car? So then I can say, okay, the mass of the car is 600 kilograms, but that doesn't go there. So what is Fg? And Fg is equal to mass times gravity, or Fg equals to mg. And so Fg is equal to 600 kilograms times the negative 10 newtons per kilogram. And I get Fg is equal to a negative 6,000 newtons. So this will be equal to a negative 6,000 newtons. And that will be equal to a positive 6,000 newtons because they will cancel out. Is there anything else that we need there? I don't think there's anything else we need there. I think I answered the question. So actually his big friend is a big friend is 200 kilograms. That's a real big friend because we have 600 kilograms minus the car. So 600 kilograms is the total minus the car, which is 400 kilograms, equals the big friend at 200 kilograms. That's a great question. And but that's not an easy one. That's not going to be a question you would get on a test. This one above is a little bit closer. I could give this one to you on a test. Right? This is like an A question on the test. This one down here, I'm just simply not going to give you one that's that hard. This might be like an honors type question. That's a good idea. Maybe I'll make this an honors question. Hey, how you got honors guys like that? Okay, so anyways, give the worksheet a try and give the quiz online a try and have a great day. If I can figure out how to stop this. Okay. Oh, let's do one more thing. Let's take a look at the quiz itself. The quiz itself in this case has some questions here with a picture, and they're pretty much all drop downs. So there's one fill in the blank, two fill in the blanks, but they're pretty much all drop down. So just kind of like look through the scenario and see what you got there. And I'm thinking I'm probably gonna add a question at the bottom that goes along with this too. So anyways, have a great day.